We stand today at the precipice of the most significant industrial transformation since the invention of the steam engine. The internal combustion era, defined by the extraction and burning of hydrocarbons, is yielding to the electrochemical age. This transition is not merely a shift in fuel sources. It is a fundamental re-engineering of how civilization stores and utilizes energy. At the absolute center of this revolution lies a single, deceptively simple device, the lithium-ion battery. From the handheld computers we call smartphones to the electric vehicles that are reshaping global logistics and the grid-scale storage systems, stabilizing our renewable energy supply. This technology is the linchpin of the modern world. But to truly appreciate the object, one must understand its creation. We are about to enter a facility that represents the pinnacle of human manufacturing capability, a Gigafactory. This is not a factory in the traditional sense of sparks and grease. It is a cathedral of chemistry and precision. The first thing to understand about battery manufacturing is that it is a war against the elements. Specifically, it is a war against moisture. Lithium, the third element on the periodic table, is an alkali metal with a terrifying affinity for oxygen and water. If the relative humidity in this facility were to match that of a standard office building, the production would fail immediately. Water vapor reacts with the lithium salts used in the process to form hydrofluoric acid, a highly corrosive compound that eats away at the internal structure of the battery and poses severe safety risks. Therefore, the air you see in this footage is not normal air. It has been processed through massive desiccant wheels, driving the dew point down to -40 or even -50 degrees Celsius. This creates an environment drier than the driest deserts on Earth. The atmospheric pressure is kept slightly positive to ensure that when a door opens, air rushes out, never in. Every technician walking these floors is wearing specialized anti-static clothing, not just to keep the product clean, but to prevent electrostatic discharge, which could ignite the volatile organic solvents used in the early stages of production. The journey of the electron begins with the raw materials. We start with the cathode, the positive electrode. In the high-performance cells used in long-range electric vehicles, the chemistry of choice is predominantly lithium nickel manganese cobalt oxide, or NMC. This is a complex crystal structure where every atom plays a specific role. Nickel is the workhorse. It provides the high capacity that translates to range. Manganese is the skeletal support. It provides thermal stability and safety, ensuring the crystal structure doesn't collapse under heat. Cobalt is the stabilizer. It ensures the ions can move freely over thousands of sharp cycles. These materials arrive as micron-sized powders, engineered with specific particle size distributions to maximize packing density. On the other side of the equation is the anode, the negative electrode. For decades, the industry standard has been graphite, a crystalline form of carbon. Under a microscope, graphite looks like a stack of dinner plates. During charging, lithium ions flow from the cathode and insert themselves between these plates, a process called intercalation. However, the industry is pushing limits. We are now seeing the introduction of silicon into the anode. Silicon is a magical but difficult material. A single silicon atom can hold 4 lithium atoms, whereas it takes 6 carbon atoms to hold just 1 lithium atom. This offers a theoretical capacity 10 times higher than graphite, but silicon swells by 300% when charged, which can crack the electrode. The manufacturing process we are about to see is designed to manage these incredible physical stresses. We enter the mixing hall, the kitchen of the battery. Here, the dry powders meet the liquid solvents. This is widely considered the most critical step in determining the final quality of the cell. If the mix is poor, the battery is doomed. We use massive planetary mixers that can handle thousands of liters of material. For the cathode, we mix the NMC powder with a binder, typically polyvinylidene fluoride, or PVDF, and a conductive additive like carbon black. The solvent used here is N-methyl 2-pyrrolidone, or an MP. This solvent is chosen because it can dissolve the PVDF binder and create a stable suspension. The mixing process involves a complex sequence of dry kneading and wet dispersion. The blades of the mixer rotate on their own axis while orbiting the tank, creating chaotic shear forces. The goal is to break up any agglomerates, clumps, or particles and coat every single grain of active material with a nanometer-thin layer of binder. This ensures that the particles stick together and that electricity can flow between them. We are looking for a specific rheology, non-Newtonian fluid behavior, where the viscosity changes depending on how fast the fluid is flowing. This slurry must be perfectly homogeneous. A single air bubble trapped in this thick black paste effectively creates a dead spot in the battery, leading to localized heating and potential failure years down the line. The slurry is pumped through magnetic filters to catch any rogue iron particles before moving to the next stage. The slurry is now pumped to the coating line. This is where chemistry meets fluid dynamics. We need to apply this liquid energy onto a solid current collector. For the anode, we use copper foil because it is stable at low potentials. For the cathode, we use aluminum foil because it resists oxidation at high potentials. These foils are incredibly thin, often ranging from 6 to 10 micrometers. To put that in perspective, a human hair is about 70 micrometers thick. The machine uses a slot die coating head, a precision machine steel block with a microscopic slit. The slurry is pumped through this slit, creating a continuous curtain of liquid that lands on the moving foil. The physics here are mind-boggling. The fluid surface tension, the pump pressure, and the web speed must be perfectly balanced to prevent defects like pinholes or streaks. We are applying a wet coating that must be uniform to within less than 1 micrometer across the entire width of the roll. As the foil flies through the machine at speeds up to 80 meters per minute, it passes under beta ray or X-ray scanners. These sensors measure the aerial density, the weight of material per square centimeter. If the coating is too light, the battery lacks capacity. If it is too heavy, the lithium ions will struggle to penetrate the deep layers, causing high resistance. The machine uses a feedback loop to adjust the pump speed in milliseconds, constantly correcting for any deviation. Immediately after coating, the wet foil enters the drying tunnel. This is a massive oven, often over 100 meters long, divided into multiple temperature zones. We cannot simply blast the wet foil with maximum heat. If we did, the solvent on the surface would evaporate instantly, forming a crust. This would trap wet solvent underneath, which would later burst out, creating craters in the electrode surface, a defect known as the orange peel effect. Furthermore, rapid drying causes binder migration, where the lighter binder molecules float to the surface, leaving the bottom layer brittle and prone to deformation. Instead, the temperature profile is shaped like a bell curve. It starts gentle to warm the mass, peaks in the middle to drive off the bulk of the solvent, and tapers off at the end to anneal the coating. The NMP solvent evaporated from the cathode is toxic and expensive, so it is never vented to the atmosphere. It is captured by a recovery system, condensed, distilled to remove impurities, and recycled back to the mixing. This closed-loop system is essential for the economic viability of the factory. By the time the foil exits the dryer, it is a solid composite electrode. The machine flips the foil over and repeats the entire coating of the dryer. Process on the reverse side, creating a double-sided active material structure. The dried electrode is now a long, continuous roll, but it is not yet ready. At a microscopic level, the coating is like a sponge, porous and fluffy. The particles are loosely packed, which means electrons have to jump across gaps to travel. This creates high electrical resistance. To fix this, we proceed to calendering, also known as the rolling press. The foil is threaded between two massive mirror-polished steel rollers. These rollers exert hydraulic pressure amounting to tons per linear centimeter. The goal is to crush the coating, reducing its thickness by approximately 30 to 40%. This process increases the energy density, packing more active material into it. Same volume, and improves the electrical conductivity by forcing the particles into physical contact. However, it is a delicate balance. We need to maintain a specific porosity, usually around 30%. These microscopic pores are crucial because they will later be filled with liquid electrolyte. If we compress the electrode too much, we close off these pores, and the ions will have no path to swim through, rendering the battery useless. This property is called tortuosity, the twistiness of the path an ion must take. Engineers spend careers optimizing this single variable. The rollers themselves must be temperature-controlled and machined to tolerances where even a deflection of 1 micron is unacceptable. With the electrode density set, we move to slitting. The large mother roller, which can be over meter wide, is sliced into narrow strips corresponding to the specific cell factor being used. While this sounds like a simple cutting operation, it is one of the most common sources of battery failure. We are cutting a composite material made of metal foil and ceramic-like powders. Traditional rotary knives rely on shearing force, but as the blade dulls, it can tear the metal rather than cutting it cleanly. This leaves behind Burrs' microscopic jagged edges of copper or aluminum. In the microscopic world of a battery, a burr is a spear. If a copper burr is left on the anode edge, it can puncture the thin separator layer and touch the cathode, causing a hard short circuit and potentially a thermal runaway event. To mitigate this, modern factories are increasingly moving to laser slitting, which uses high-intensity light to ablate the material, leaving a sealed, burr-free edge. Regardless of the method, the slit strips pass through automated optical inspection systems. High-speed cameras photograph every millimeter of the edge, using algorithms to identify and flag any imperfections. Before assembly, the slit rolls undergo a secondary vacuum drying process. Despite the earlier drying tunnel, the electrodes may have reabsorbed trace moisture from the factory. They're baked in vacuum ovens for 12 to 24 hours to bring the water content down to parts per million levels. We then enter the dry room for assembly. Here, the anode, cathode, and the separator meet at the winding machine. The separator is a microporous polymer film, typically polyethylene or polypropylene. It acts as an electrical insulator, but an ionic conductor. The winding machine spins these 3 layers into a tight spiral, known as the jelly roll. The alignment here is critical. The anode must physically overhang the cathode by a few millimeters on all sides. This is a safety feature. When lithium ions travel from the cathode, they must find a corresponding spot on the anode to intercalate. If the cathode were to overhang the anode, the ions would have nowhere to go and would plate out as metallic lithium on the edge. These lithium dendrites grow like tree roots and can pierce the separator, killing the cell. The winding tension is also strictly controlled. Too loose and the layers separate. Too tight and the electrode coating cracks at corners. Once the jelly roll is removed, we must establish the electrode connections. We use ultrasonic welding to attach metal tabs to the raw foil sections of the electrodes, usually aluminum for the positive and nickel or copper for the negative. Ultrasonic welding uses high-frequency mechanical vibrations to create a solid-state weld without melting the metals, which prevents thermal damage to the surrounding components. The jelly roll is then inserted into the cell casing. For cylindrical cells, this is a nickel-plated steel can. The can provides mechanical robustness and acts as the negative terminal. The insertion process must be smooth to avoid tearing. The outer separator layer, which would short the cell to the can. Once inside, the center pin is often inserted into the hollow core of the winding. This pin provides structural rigidity, preventing the jelly roll from collapsing inward during rapid discharge, and also serves as a chimney to allow gases to escape to the vent in the event of failure. The internal tabs are then welded to their respective terminals. The anode tab is welded to the bottom of the can, and the cathode tab is welded to the top cap assembly. The top cap is a sophisticated component containing the current, interrupt device, CD, and the positive temperature coefficient, PTC, switch. The CD is a pressure-sensitive mechanical fuse. If the battery generates gas due to overcharging or a fault, the internal pressure pushes a metal disc up, snapping the electrical connection and permanently disabling the battery before it can explode. The PTC acts as a reversible thermal fuse, increasing resistance if the current gets too high. The cap is then crimped onto the can with a polymer gasket to create a hermetic seal. To ensure the seal is perfect, we perform a helium leak test. The cell is placed in a vacuum chamber and bombarded with helium gas. Helium atoms are so small they can penetrate leaks that water or air molecules cannot. A mass spectrometer detects if any helium enters the cell, ensuring the integrity of the enclosure for the lifespan of the product. The battery is now mechanically complete, but it is electrically dead. It is a dry assembly. To activate it, we must add the electrolyte. This is a solution of lithium salts, typically lithium hexafluorophosphate, dissolved in a blend of organic carbonates. The cells enter a vacuum chamber, and the electrolyte is injected through a precision nozzle. Because the jelly roll is bound so tightly, the liquid does not simply soak in. It sits on top. We must use vacuum cycling alternator between vacuum and atmospheric pressure to force the liquid into the microscopic pores of the electrolyte. This process is called wetting. It is a time-consuming step, but absolutely vital. If there are dry spots on the electrode, those areas will not participate in the reaction. This forces the current to concentrate in the wet areas, causing localized heating and rapid degradation. The wetting process is optimized by the selection of separator materials with high affinity for the electrolyte and by precise control of the vacuum cycles. Once wetted, the battery moves to formation. This is the first time the battery is charged. It is not merely a quality check. It is an electrochemical manufacturing step. When a cell is charged for the first time, the electrolyte reacts with the graphite anode to form a solid layer called the solid electrolyte interface, or SEI. This layer is critical. It acts as a passivation layer, preventing electrolyte from continuously decomposing while still allowing lithium ions to pass through. The quality of the SEI layer dictates the cycle life of the battery. If the formation current is too high, the SEI will be porous and unstable. If it is too low, the process takes too long. Manufacturers use proprietary charging protocols, stepping current and voltage up in precise increments to grow them. Perfect SEI crystal structure. During this process, a significant amount of gas is generated as a byproduct of the SEI formation. In cylindrical cells, this gas is usually absorbed or accommodated by the void volume. In pouch cells, it is collected in a gas bag that is cut off later. After formation, the cells are fully charged and chemically active. They are then moved to the aging warehouse. This is a massive storage facility where millions of cells sit on shelves for a period ranging from 1 to 4 weeks. This is a quarantine period. We are monitoring the cell discharge rate. Every battery loses a tiny amount of charge over time due to internal chemical reactions. However, if a cell has a microscopic defect, like a tiny metal burr piercing the separator just slightly, will create a micro short that drains the battery faster than normal. By measuring the voltage drop of every single cell over the aging period, we can identify these outliers. A cell that drops 1 volt more than its peers is a fire hazard waiting to happen and is ruthlessly cold. This aging process is often done at elevated temperatures to accelerate the chemical reactions and explode. Defects soon. The survivors of the aging process move to the final grading stage. Despite the incredible precision of the manufacturing process, there is always slight variance in the final capacity of the cells. One cell might hold 4995 milliamp hours, while the next holds 5005. For single-cell applications like a flashlight, this doesn't matter. But for an electric vehicle battery pack, which puts thousands of cells in series and parallel, consistency is everything.
If the cells are mismatched, the pack becomes unbalanced, limiting its total range to that of the weakest cell. Therefore, the grading machine charges and discharges the cells to measure their exact capacity and internal resistance, asserted DCM. The cells are then sorted into highly specific bins based on their performance. Only cells from the same bin will be welded together into a module. This ensures the pack operates in perfect harmony. Finally, the cells are visually inspected, wrapped in heat shrink insulation, labeled with a QR code containing their entire manufacturing history, and packed for shipping. What we have witnessed is the transformation of raw geology into refined energy. Storage, from a mining of lithium and cobalt to the nanometer precision coating, the heavy industrial pressing, and the delicate electrochemical formation. Every step is a link in a chain that cannot break. This facility is more than just a factory. It is the foundry of the 21st century. As the world moves away from the combustion engine and toward a renewable future, the importance of these blue and silver cylinders cannot be overstated. They are the silent engines of our new world, mass-produced by the billions, enabling a cleaner, quieter, and more electrified human experience. This is the reality of modern manufacturing. This is how we power the future.